Okay, so welcome back, and this is the first in our series of videos looking at halogenoalkanes. So you'll need the halogenoalkanes pack, and we're going to be going through the first section of it. That's going to be looking at naming halogenoalkanes and their physical properties. Okay, so we're on to the notes now, and we're looking at the three types of halogenoalkanes. Now this is very similar to alcohols in that we have primary and secondary and tertiary alcohols. We also have primary, secondary and tertiary halogenoalkanes. So a primary halogenoalkane has one R group, in this case one R group and one halogen. In secondaries, we've got two R groups. That's my R group on that one. My two R groups and my halogen. And tertiaries have three R groups and my halogen. Now, the X can represent any halogen, so there could be fluorine, chlorine, bromine, or iodine. And the R's can represent any carbon chain, so it could be a CH3 group, it could be an RR group, which is what we call a benzene ring, but they can be the same with the difference, but they've got to contain at least one carbon. The only exception to that is the methane molecules. So I'm going to look at the first two examples, chloromethane and 1,1-dichloroethane, and then I'm going to get you to do them. So chloromethane, very simply, meth means I've got one carbon, and I've been told I've only got one chlorine, so that's the displayed formula of chloromethane. The skeletal formula, well, we don't show carbon to hydrogen bonds, we don't show hydrogen atoms, and we only show carbon-carbon bonds as a straight line. Well, we've only got one carbon, but we do show this bond, so basically what I'm going to have is a straight line representing the bond between the carbon and the chlorine. The next one, 1,1-dichloroethane. So this time, eth, I've got two carbons, I have a dichloro, that means I've got two chloro groups, and they are both on position 1, so they're both on the first carbon. Doesn't matter which carbon I make the first one, because I always number them from the lowest possible number. Okay, so that's what my 1,1-dichloroethane would look like. The skeletal formula, I've done the wrong box, but there we go, skeletal formula. Well, you've got your carbon-carbon bonds, and then you've got the Cl and the Cl. So that's my skeletal formula for those two. I know I've put them in the wrong box, sorry. Right, your go. Can you have a go at doing the others? Okay, there are some very good websites and other YouTube videos for you to look at, which will take you through this in the PowerPoint as well. Okay, so this is what you should have drawn for the others. So going down this side, I've got chloromethane, which is a primary. I've got two bromobutane, and this is a secondary because I've got two R groups here and my hydrogen. This one here, 2-bromo-2-methyl-propane, well, that's going to be a tertiary because I've got 1, 2, 3 R groups for the carbon of the halogen. In the last case here, this again is actually a secondary because I've got two R groups and this hydrogen here. We're not asking you about whether they're primary, secondary, tertiary down this side. It's a little more complicated. This first one we did. Second one, 1,2-dichloro. The only difference between these two is the fact that instead of both chlorines being on the first carbon, I've got one on the first and one on the second. And then the last two involve a double bond. So we've got a Z and an E version. Here, because the chlorines have highest priority, this is my highest priority group out of these two, and this is highest priority out of these two. So this is my Z version. Okay, so in halogenoalkanes we have that electronegative fluorine, chlorine, bromine or iodine. This makes the C halide bond, the CX bond, polar because the carbon will be delta positive and the halogen will be delta negative, as all of them have a higher electronegativity than carbon. This means that the intermolecular forces, well, they all have London forces, forces because everything has London forces, but in addition to that, they also have permanent dipole, permanent dipole. What they do not have is they do not have hydrogen bonding. They are immiscible in water as they don't have hydrogen bonding. They do dissolve quite well in organic solvents like alcohols. Alcohols are very good co-solvents. That means that they can take a wide range of things into solution, both polar and non-polar. So if we look at their trends in boiling points, and we've got three things to look at. We've got to have a look at the increase in carbon number. So that's this graph here. We've got to look what happens when we go down the halogen group. And we've got to have a look at here is the effect of whether it's a primary, secondary or tertiary halogenoalkane. So I'm going to start here with the increased chain length. And I'm going to use iodoalkanes as my example. So as we increase the number of carbon atoms, we increase the boiling point. So the more carbon atoms you have, the higher the boiling point. The reason for this is the same as it usually is. More electrons means stronger London forces. Stronger London forces means a higher boiling point. So as carbon chain increases, you get more electrons, therefore stronger London forces, therefore more energy required to separate the molecules. So that's basic intermolecular forces. We've got more electrons means stronger London forces means more energy required to separate them. Now, we have exactly the same pattern when we look at the halogen. So as we go from fluorine to chlorine to bromine to iodine, we should notice that the boiling point increases. And this is for exactly the same argument. Iodine has more electrons than fluorine, therefore it has a stronger London forces, therefore it needs more energy required to separate them. The polarity of the bond does not impact on the boiling temperature here because it's permanent dipole-dipole interactions, and yes, they get weaker as we go from fluorine, chlorine, bromine to iodine, but that's more than offset by the increase in electrons because remember the London forces dominate compared to permanent dipole, permanent dipole. The last one we're going to talk about is this graph, which looks at primary, secondary and tertiary halogenoalkanes. And as you can see, there is a very similar trend no matter which one we are dealing with. Now, in these cases, they've got all the same number of electrons, so that can't be impacting on the London forces, but they are changing in the amount of branching. So a primary halogenoalkane has less branches than a secondary, which has less branches than a tertiary. So this is our branching effect, our packing effect. So in this case, the tertiaries can't pack as efficiently together. That weakens the London forces, therefore less energy is required. You can think of one of the halogens as acting a little bit like a methyl group because they're quite bulky. So the secondary here, where the bromo group is sticking out the side of the molecule, you will get some branching, but the tertiary will have the most branching because it has the bromo group and a methyl group. So that really reduces the packing efficiency and makes the boiling point much lower. Okay, so that finishes this short video looking at the structure of the halogenoalkanes and their physical properties. In the next video, we're going to be looking at the preparation of halogenoalkanes from the alcohols, and we're going to start looking at the large core practical, the preparation of bromobutane from butan 1-ol. But that's all for now. Take care, stay safe. Bye-bye.